A university-published greenhouse design grows food year-round. No electricity, no heating fuel, no soil amendments required. It costs under $200. Most Americans cannot legally build one. The building code will not allow it. A commercial greenhouse runs $5,000 to $50,000 to build. Then you pay $500 to $2,000 every single year just to heat it. The structure we are covering today uses the earth itself as its furnace. Total cost, the price of a shovel and some salvaged windows. By the end of this video, you will know exactly how to design, excavate, and plant a Walipini. And you will know how to navigate the codes standing in your way. Welcome. This channel exists for one reason. Critical survival knowledge is disappearing, well, not because it stopped working, because it stopped being profitable. We dig it back up, we document it, we put it in your hands. If that mission matters to you, subscribe now, not for the algorithm, for the archive, because we are building something here that matters more than metrics. This design did not come from a YouTube comment section. It came from one of the most respected agricultural institutes in the country, and it was built for people who had nothing. In 2002, the Benson Agriculture and Food Institute at Brigham Young University published a technical paper. The subject was a subterranean greenhouse deployed on the Bolivian Altiplano, 12,000 feet above sea level, freezing winters, brutal wind, intense solar radiation, extreme poverty. The communities there needed a way to grow food year-round with no money, no electricity, and no imported fuel. The Benson team delivered exactly that. They called it the Walipini. The word comes from the Aymara language. It means place of warmth. But the Benson Institute did not invent this idea. They refined it, they documented it, they gave it engineering specifications. The principle behind it is older than any university on Earth. In Korea, farmers built unheated growing pits centuries ago. They buried their cultivation space below grade. The earth held warmth. The crops survived winter. In ancient Persia, engineers constructed yakchals, massive underground chambers that used thermal mass to store ice in the desert. The same physics, different application. In colonial New England, American farmers dug pit greenhouses into hillsides. They angled glass southward. They grew greens through Massachusetts winters. No furnace, no coal, just earth and sun. Indigenous cultures across 4 continents independently discovered the same principle. Bury your growing space. Let the ground do the work. The Benson Institute gave it a name and a blueprint. But the reason it works is something you can measure with a thermometer and a shovel. If you are the kind of person who does not stop at one video, the vault exists for you. It is the deep archive behind everything we publish. Complete breakdowns on water purification, food preservation, off-grid energy, medical preparedness, and structural survival design. No filler, no fluff, just the information that matters when systems fail. The link is below this video, but stay right here, because what comes next is the physics that makes the entire Walipini possible. And once you understand it, you will never look at your backyard the same way. Now, the physics. Dig 6 feet into the earth in most regions of the United States. The temperature down there holds steady near 55 degrees Fahrenheit. Year-round, summer, winter, it does not matter what the air above is doing. At 6 feet of depth, the ground maintains a nearly constant thermal state. This is not speculation. This is measured, published data. The United States Department of Agriculture tracks soil temperatures across every climate zone. At shallow depths, temperatures swing with the seasons, but below 4 to 6 feet, those swings flatten. The earth becomes a thermal battery. It absorbs heat slowly, it releases heat slowly, and it holds a baseline that sits above freezing 365 days a year in most of the continental United States. This is the same principle behind root cellars, behind cave storage, behind earth-sheltered housing, behind military bunker design, behind the Svalbard Global Seed Vault in Norway. Every one of those structures exploits the same physical law. The ground is a massive, slow-moving heat reservoir, and it is free. A Walipini taps that reservoir by placing the growing space below grade. The earth walls radiate their stored heat inward. The floor conducts warmth upward. And the glazing on top, angled toward the sun, lets solar radiation in to charge the thermal mass during the day. Think of it as a greenhouse that heats itself from below instead of from above. The sun adds energy. The earth stores it. The cycle is passive. No fans, no thermostats, no propane. But the glazing angle matters. It must be calculated relative to your latitude. Too steep, and winter sun bounces off instead of entering. Too shallow, and summer sun overheats the interior. The general rule is your latitude plus 15 to 20 degrees from horizontal for winter optimization. This is not guesswork, it is geometry. And here's the critical design variable most people get wrong. The ratio of thermal mass to glazing area. Too much glass, and the space overheats during the day, then crashes at night. Too little glass, and the solar gain is insufficient to charge the thermal mass. The balance is what separates a functioning Walipini from a cold, damp hole in the ground. But there is a problem that kills most underground greenhouses before the first harvest. Humidity. Below grade, moisture accumulates. Warm air holds water vapor. When that air contacts cool earth walls, condensation forms. Condensation breeds mold. Mold breeds fungal disease. Fungal disease destroys crops. This is not a minor inconvenience. It is the #1 failure mode in underground growing structures. The solution is not opening a window, it is designing convective circulation from the start. A vent placed low on the windward side. A vent placed high on the leeward side. Cool air enters low, warms as it rises. Exits high. This creates a passive airflow loop that removes excess moisture without requiring electricity. The vents must be closable for cold nights, but the system must be built into the structure. It cannot be added later, so the physics work. The history proves it. A major university published the blueprint. So why are these not in every backyard in America? Because the International Building Code has something to say about holes in the ground. Any below-grade occupied structure in most U.S. jurisdictions triggers a cascade of code requirements. Engineered drainage systems, structural certification for earth retention walls, egress provisions for below-grade occupied spaces, and here's the one that finishes it. Stamped plans from a licensed engineer or architect. Let those words settle. A structure designed for impoverished Bolivian farmers who had no money, no electricity, and no options now requires a licensed professional engineer to approve it before an American homeowner can legally dig the first shovelful. The permit process alone can cost more than the greenhouse. Filing fees run hundreds of dollars. An engineer's stamp costs hundreds to thousands more. The drainage study adds to the total. The structural calculations add further. By the time you satisfy every code requirement, a $200 greenhouse costs $2,000 to $5,000 in paperwork and professional fees. The primary advantage, the one that makes it revolutionary, is erased. Now ask who benefits from that erasure. The commercial greenhouse industry is a multi-billion-dollar sector. Heating systems, automated climate controls, proprietary glazing products, replacement parts, fuel, ongoing supply chains that generate recurring revenue every single year. No corporation on earth profits from a $200 structure built with salvaged windows and manual labor. You cannot patent a hole in the ground. You cannot trademark thermal mass. You cannot create a subscription model for sunlight. Every Walipini that gets built is a customer who never enters the commercial greenhouse pipeline. Ever. This is not necessarily a coordinated conspiracy, but the incentive structure is unmistakable. The codes were not written to suppress Walipinis specifically. They were written to regulate construction broadly, but the effect is identical. A structure that costs nothing, requires no proprietary components, uses no purchased energy, and produces food indefinitely is functionally illegal for most Americans. Not because it is dangerous, because the regulatory framework was never designed to accommodate something this simple. 3 generations of supermarket dependence have not helped. Most Americans alive today have never grown a single calorie of their own food. The knowledge base has atrophied. And the regulatory environment ensures it stays that way. Some states offer agricultural exemptions for structures used exclusively for crop production, but those exemptions are jurisdiction-specific. You must verify with your county before you build. That is not a disclaimer. That is a survival instruction. Now you know what you are up against. Here's what you actually need to know to build one. If this is the kind of information you think should exist on this platform, hit subscribe, share this video. The next section is the construction walkthrough. It is what you came here for, and it starts now. But first, honesty. A Walipini is not magic. It has real constraints, and I'm not going to hide them from you. Flooding is the most serious risk. If your water table is high or your site drainage is poor, water will enter the pit and destroy your growing beds. Full stop. Test your site before you dig. Sandy or loose-fill soil can collapse. You need stable earth walls or you need to reinforce them. The humidity problem I already described will ruin crops if your ventilation design is inadequate. The interior temperature range sits between 45 and 65 degrees Fahrenheit in most climates. That excludes warm season crops. Tomatoes need 70 to 85 degrees Fahrenheit. Peppers need the same range. Cucumbers will not thrive. This is not a tropical greenhouse. It is a cool season-growing chamber. Light levels below grade are lower than an above-ground greenhouse. Your crop selection must account for reduced photosynthetically active radiation, and rodents will find their way through earth walls if you do not line them. Those are the real constraints. Here is how to build one that accounts for every single one of them. Site selection comes first. You need a location with good drainage, not flat ground where water pools. A gentle slope is ideal. Test your soil. You need stable clay or loam. Sandy ground requires reinforcement. The long axis of your pit must run east to west. The south-facing wall will hold your glazing. That south face needs unobstructed sun exposure from 9 in the morning to 3 in the afternoon at the winter solstice. Not summer, winter solstice. That is your minimum solar window. If a tree line or building shades that face in December, Pick a different site. Excavation. Dig 4 to 8 feet deep. Deeper is warmer but harder to dig and harder to access. 6 feet is the most common working depth. Width runs 6 to 8 feet. Length runs 12 to 20 feet, depending on your needs and your willingness to dig. The north wall stays at full excavation height. The south wall is cut lower to accept the glazing angle. The difference in height between north and south walls determines your roof pitch and your solar gain angle. Line the floor with gravel, 4 to 6 inches deep. This is your drainage layer. Over the gravel, lay landscape fabric to prevent soil migration into the drainage. Your earth walls can be left raw in stable clay. In less stable soil, use stacked sandbags, cinder blocks, or rough-cut timber to retain the walls. Line the interior face with plastic sheeting to manage moisture migration. This also deters rodents. Glazing, salvaged windows work, 6mm polyethylene sheeting works. Polycarbonate panels are the best option if your budget allows. The critical detail is double-layer construction with an air gap between layers. A single layer of glazing loses too much heat at night. 2 layers with a 1-inch air gap between them dramatically improve thermal retention. Frame your glazing on a simple wood structure running the length of the south-facing opening. Angle it according to your latitude. Seal the edges. Every air leak is a heat leak. Ventilation. Install a vent low on the east wall. Install a vent high on the west wall. Size them at minimum 6 inches by 12 inches each. These create your convective loop. Make them closable with sliding covers or hinged flaps. Open during the day when humidity rises. Close at night when you need to retain heat. Growing beds, you have options. Direct soil beds work if you amend the native soil with compost. Straw bale beds provide excellent drainage and insulation. You can fill raised frames with compost-heavy growing media. Simple passive hydroponics using 5-gallon buckets with wicking reservoirs work in this temperature range and eliminate soil-borne disease entirely. What to plant? Lettuce, spinach, kale, Swiss chard, arugula, carrots, radishes, beets, turnips, garlic, green onions, sorrel, perennial kale varieties that come back year after year. Herbs including cilantro, parsley, chives, and mint. These crops thrive in the 45 to 65 degree Fahrenheit range. They tolerate lower light. They produce food month after month, year-round, with no electricity and no heating fuel. That is a year-round food production system for under $200. Let me put this together for you. A structure validated by thousands of years of human practice across 4 continents, published by a major university, backed by measurable, repeatable thermal physics, capable of producing fresh food every month of the year with no electricity, no fuel, and no ongoing cost. A structure that costs less than a single trip to the emergency room. And for most Americans, building one requires more money in permits and engineering fees than the greenhouse itself cost to construct. That is not a failure of engineering. It is a failure of priorities. In any extended disruption to the commercial food supply, the ability to grow food without purchased inputs is not a lifestyle preference. It is a survival capability. And you now possess the knowledge to build one. The physics, the history, the construction method, the crop list, the limitations, all of it. This information stays alive only if it moves. Share this video with one person who grows food, one person who thinks about preparedness, one person who has a backyard and a shovel. That is how critical knowledge survives. Not in archives, in practice. Next week, we are covering a water purification method that predates modern chemistry by centuries. Same pattern. Proven. Published. Suppressed by economics. You do not want to miss it. Stay informed. Stay prepared. Stay building.